So to reiterate, before I was interrupted, we have ionic compounds formed by the transfer of electrons, where when you gain or lose electrons, you lose or gain charge respectively, and when you have opposite charges can attract and hold a molecule together through electrostatic interactions. The other major type of bond is the covalent bond, and this is where you have a bond formed by the sharing of electrons. For example, in one of the halogens in group 7, like chlorine, it has 7 electrons, it wants to have 8. It finds another chlorine atom that has 7, it wants to have 8. They both need one more. They say, why don't we share a pair? And they share those electrons, and we can envision those electrons as interacting and holding the molecule together. Sometimes you get 1 pair, 2 pair, or 3 pair of electrons interacting to hold it together in a covalent bond, but as we explained, and as I'll explain later when I do a little lecture on water with some demonstrations, those electrons are like my children. They say they're going to share, but they don't share fair. They don't share equally. And the reason some atoms don't share equally is because of their electronegativity. If they're highly electronegative, that means they're electron withdrawing, they draw electrons into themselves, they'll attract electrons into themselves, and so those covalent molecules have an unequal charge distribution, so they have a negative side and a positive side. The electronegative atom has pulled those electrons into itself, and it has a greater share of electrical charge. It has more time with the electrons, if you will. The electrons are closer to it. They're associated with it more than with the other atom. And so it gets a slightly negative charge. The other atom becomes kind of electron deficient, partial positive. Now overall the charge is completely neutral, but the molecule becomes polar with a positive and a negative pole, like a battery. Probably really more like a capacitor, but it's analogous to something like a magnetic pole. I have some models of water here, and that's what I'm going to talk about next, are models where the oxygen is one of the most electronegative atoms, second only maybe to fluorine. But it pulls those electrons it's sharing with the hydrogen atoms into itself, leaving the oxygen side of the molecule slightly negatively charged, and the hydrogens have a partial positive charge. Well, you have positive and negative, you have opposite charges, and opposites attract. Now, of course, that's a magnet, but the concept is similar. Now, rather than go back through polarity, I just want to cover a few things where I was expecting to have access to some materials that, because of the move, because of the Tech Center South being torn down, because of the changes in the procedures for having materials and for our loss of our posters in our classroom, I wasn't able to explain and demonstrate some things like I want. So let me go back to a few parts of our talk for a few minutes and show you what I had hoped to show you before. So we're back in chapter 3, and one of the things we're doing constantly is modeling, and we'll be describing chemical formulas, and you'll be working on a lab soon, and at the end of the chapter we'll cover 2 things: taking a chemical formula and writing the name, and taking the name of a compound and writing its chemical formula. And so CO2 is carbon dioxide. It doesn't tell you it's carbon dioxide. You would have to know the rules for naming. And CO2 is one carbon and two oxygens, but it doesn't tell you how they're put together, how they're connected. Now, anyone with a little basic chemistry knowledge is going to know how they're connected, but I'm going to show you some other things. H2O is a structure for water, but it doesn't tell you how they're connected. When you write a structural formula, it tells you that the H is connected to the O, which is connected to a different H. And so it tells you a lot about its structure. But it also leaves out a lot of detail about its structure. For example, how close are they together? What are the dimensions? What are the bond angles involved? And how are these connected? So we have several different models. I have some examples of them here. We have classic ball and stick models, and since they're using methane here, I will use methane. Here's a, forget what it's called, polymold ball and stick model, and of methane, CH4, one carbon in the center with 4 hydrogens attached to it, each one at a 109.5 degree angle relative to the others. This is a classic, we're going to be doing some labs with these, ball and stick model. It may not seem like much, just some wooden dowels and some wooden balls painted different colors. In this case, carbon is black, hydrogen is, in this case, is yellow. Sometimes it's white, but in this model, these balls are actually have their holes drilled plus or minus a half a degree of angle in accuracy. And the bond lengths, when you put them out there, are also very accurate when you do the conversion factor. I forget how many centimeters equal an angstrom, or a nanometer or picometer, since I'm not supposed to use angstroms anymore. So one thing though, we know in a ball and stick model, electrons don't spin around this hydrogen and then come spin around this carbon and then come back up to this little wooden dowel. That's not a true, realistic representation of how these appear. So we also have space filming models which try to delineate or to illustrate the limits of the electron cloud, where that region where you have a high probability of finding an electron. And so they tend to depict the shape and be probably quite a bit more accurate in representing the true nature of the molecule. So once again, unless you have Superman glasses and can put them on and look at it, we don't know for sure how they look. Before I go into more bonding, I wanted to cover a few things using these models about how you tell if something's going to be polar or non-polar, covalent. Okay? So sometimes these bonds are not shared equally, and we have some molecules that are extremely electronegative. The general trend is electronegativity increases left to right across the periodic table, because as you go left to right, you're getting more protons in the nucleus that can pull electrons into it more. You have more positive charge to attract the negatively charged electrons. So you have electron withdrawing principles. But the electronegativity goes down, as you go down the periodic table, as you go down a group or a family and go into the higher level periods. And that's because those electrons are getting further and further and further away from that positively charged nucleus. And as we saw, that attraction decreases with the square of the distance, decreases very quickly. We'll also talk about shielding in the next chapter, but we are decreasing in electronegativity. The way I like to tell students to remember the trend, though, is Fluorine's the most electronegative element, with electronegativity of 4. And the closer you are to fluorine, the more electronegative you are. So, and as you can see in general, metals are not electronegative. Fluorine is, and being a biochemist, many of the molecules of life are very electronegative, specifically nitrogen, oxygen, sulfur, and phosphorus. And that has important implications in higher level courses. So, when we say you're either ionic or you're covalent, what we find is that it's not one or the other, it's a continuum. So the covalent bonds sometimes get very polar and sometimes get so polar they're practically charged. Classic example is hydrogen fluoride gas. In fact, put it into water and it becomes ionic and becomes hydrofluoric acid. So even the ionic bonds don't have pure ionic character with, total simple electrostatic charge and interaction. The other things I wanted to talk about and didn't get a chance to demonstrate are the types of bonds that we come across. And I wanted to talk about, when we talk about ionic bonds, two things that will become important when we name them, and that is, you need to know the charges on the individual ions. And it's very simple for the group A elements. If you're a group A metal, your charge is equal to your group number. And if you're a group A non-metal, the charge is equal to your group number minus 6. Then, the other thing I want you to know is that when you put these ions together to form an ionic compound, yes, you're dealing with lots of charges, but overall the molecule has to be neutral. So we need to balance our charges when we put these together to form a compound. I talked about ionic size and various things, and we discussed that if you look at the energy in compounds, that they like to be compounds, it's energetically favorable for them to be compounds. And here's your percent ionic character, even on things you would think are 100% ionic, like sodium chloride or hydrogen fluoride. You see that they have a percent ionic character ranging from 50% up to maybe 85%. Nobody's 100% pure ionic. No one's pure, well, probably if you are a binary compound, not a binary compound, I'm sorry, but if you're a compound like O2 or H2, we have two identical atoms coming together, then there is no polarity in the bond. You are purely covalent. So, I talked about models. I want to talk about bond length and bond energy. And so, we have three types of bonds in the world. Single bonds. Here's hydrogen. Two hydrogen atoms come together, form H2. Why? Each hydrogen has one electron. They want to have two like helium, like the noble gas. So, this one has one electron, this one has one electron. They both want to have two. They say, why don't we share? And that's exactly what they do. They share and form a single bond between them. If you look at oxygen, it's group 6, it has 6 electrons. It wants to have 8, like a noble gas, like a group 8A noble gas. And so it doesn't just want to share one, it shares 2. Now, in this case, in our ball and stick model, we depict those bonds with springs. Because if I used a rigid piece of wood here, it wouldn't work when I put the second bond in. Because remember, these bond angles are very specific. So, these electrons have to, I like the springs, I like the ball and stick model this way, because For me to make this a double bonded molecule, look what I have to do. I have to bring this in closer, and my distance decreased. And double bonds are shorter. They're also, notice I had to put some effort in to do this. I had to put some energy in here and connect that. They're also stronger than the single bond. That makes sense, right? One spring is easier to pull apart than two springs would be, right? So, a double bond, in general, is stronger than a single bond, and in general, is shorter. And if you move up to a triple bond, there aren't a lot of examples of triple bonds. My favorites, and most textbooks' favorites, are acetylene, another one cyanide. This is acetylene, the welding gas. It has two triple bonded carbons in it. And nitrogen, which is group 5. It has 5 electrons. It wants to have 8. So it shares 3 pair of electrons with another nitrogen to form N2, molecular nitrogen. The nitrogen we breathe in our atmosphere, that composes what? About 79% of our atmosphere. As you can see, these bonds, 2 bonds, I started with 1 bond, one very strong bond, and they're this far apart. Add a second bond, it grows shorter, but what happens when I add the third bond? It grows even shorter. This molecule is much shorter than my double bonded oxygen, and it's held together much more strongly. So higher energy in a triple bond and shorter distances. Your book has a table. You can see the bond energies from single bonds tend to increase as you go up to multiple bonds. Here they're between, what, a couple hundred and 500. I don't see the units here, kilocalories per mole or whatever the energy unit is here. And when we get up into the double and triple bonds, all the way up to 1,000. In general, much higher. Triple bonded nitrogen, 941 in the example I gave you. Triple bonded carbon in the acetylene, 839. That's why when you burn it, it releases a lot of energy. It gets hot enough to cut and melt steel. That's why they use it for welding instead of just plain old methane or ethane or butane. So, and the bond distances, you can see a carbon-carbon bond, 154, carbon-carbon double bond, 134, and a triple bond, 120. This bond length in picometers goes down as you as your bond changes from single to double to triple bonded. So they get much shorter. That's all I want to go back and demonstrate with some models. We'll talk about lone pairs and bonding pairs and Lewis structures in the next chapter, which basically covers bonding and the types of structures molecules can assume. A lot of this material is repeated in the next chapter, and in the interest of time and in the interest of catching up with our COVID-19 disruption, I'm going to save the rest of this chapter, except for naming, for chapter 4, where we basically reintroduce this material and talk about bonding and exceptions to the octet rule when we draw unusual Lewis structures. Our next lecture is going to be over the last section, naming simple compounds, and I'm going to have a lab set up for you to practice naming compounds, giving the formula, and writing the formula, giving the name. So let's see if we can continue making a few more videos, reaching out to one another, but also always remember, you can always call me on my cell phone, leave a message. If I don't recognize the number, I never answer, and if I'm eating or otherwise occupied or talking to someone else, and I'm always talking to someone, I don't answer. But if you leave a message, I'll get back to you as soon as I can. I love text. I don't have a lot of meetings these days, but when I'm in a meeting, I can do what y'all do during class, which is get on there, answer your questions. I want to hear from you because I want to know what your questions are. I will stop in some of these lectures and show you sample test questions, potential test questions, areas of emphasis I want you to remember. And if it's ever, you can always email me at mshanley@carc.edu. Take care, stay healthy, and I will see you in the next video.